So now if you remember Ligand exchange, Ligand exchange reactions were equilibrium reactions. So K stability, just very quickly, it's an equilibrium constant for a Ligand exchange reaction. Just 1 second. So our stability constant. Now this specific constant known as K's with stab at the end, that was simply an equilibrium constant for a Ligand exchange reaction. For Ligand exchange. Now, the thing with this is that we've already studied equations for Ligand exchange. For example, if you have copper with 6 water molecules, copper aqueous, and it's got a charge of +2, what will happen is that if you add NH3, let's say I add 4 NH3 molecules, these ligands are going to knock out the water molecules and take their place. So it's going to be copper with 4 NH3s, and they're going to be 2 water molecules. And the entire thing will have a charge of +2. And the water molecules are going to get knocked out, 4 of them. So this specific thing is a Ligand exchange equation that we did earlier as well. Now in this Ligand exchange, since it's an equilibrium reaction, equilibrium constants that would be known as K stability. It's the ratio of the concentration of the products divided by the ratio of the reactants. Okay. So Isaac, can you hear me? I sent you all the lectures, okay? For transition metals. As a product concentration divided by reactant concentration. Your products are these, and your reactants are these. So there's an equilibrium that exists between them. So if you write down the expression is going to be the concentration of the complex ion, which is copper. This one, the first one. So these are my products. So I'm going to write these. It's copper, NH3, the 4 NH3s. And there are 2 water molecules. And its concentration, this has a charge of +2. And the concentration of water, that's going to be power 4. And the whole thing would be divided by my reactants. My reactants are these 2. It's copper with 6 water molecules and 4 NH3s. Those are my reactants. So it's going to be copper with 6. As it's copper with 6 water molecules. Its concentration, and the other one is NH3. Its concentration and the power is going to be 4. So hopefully everyone remembers how to write equilibrium constants and the expression. The coefficient becomes the power. So that's K stability. Whenever you have a Ligand exchange reaction, it's an equilibrium reaction. Product concentration divided by reactant concentration. You write down the expression, that's K stability. Now, there's one thing that you should know of, and that is that when the solution is aqueous, that means, and it always applies to equilibrium constants. So remember this, in aqueous solutions. So if everything is happening in aqueous solutions, then that indicates that water is in excess. And water is in large excess. So whenever you have an aqueous solution, the amount of water kind of remains constant. it hardly changes because it's whenever something is in large excess, it becomes constant. For example, if there are 10,000 moles of water, then if a few moles are produced, or a few moles get consumed, the amount of water almost kind of remains constant. You can remember solutions are mostly water, and water is in large excess. So the moles would be kind of constant, which is why you don't write them down in the expression, because its concentration is going to be a constant. I mean, is this point clear to everyone? Bhaskar, is this clear?
Yes, sir.
Sam, is this clear?
Sir, can you explain it again?
But remember this, in equilibrium, whenever you have an equilibrium and water is aqueous, what this means is water is in large excess. So that means if you have, let's say, 0.1 moles of this particular complex, and there's 0.2 moles of this complex, and there might be a few moles of this complex that are produced, and the whole solution is made up of water. So let's say there are 1,000 moles of water. So the point I'm trying to make is that even if this equilibrium shifts forward just very, very slightly, if it shifts forward, like 0.1 moles react with 0.1 moles to produce a small amount of this, and this is produced. Okay. So the moles of water would just change very slightly. It would go from 1,000 moles to 1,000.5 moles or something like that. Okay. So the amount of moles of water there would hardly be any effect on the amount of water. Like if this reaction goes forward and the amount of moles of this particular complex double, they increase by 0.5, the moles of water would also increase by 0.5. I mean, according to the ratio, but it would increase by a very small amount, and its concentration would almost be a constant. Zaib, do you get the point?
Yes, sir.
Okay, so remember this, in all equilibrium constants, this also applies to rate of reaction. You add anything that's in large excess, it becomes constant throughout the solution. If a few moles are produced or a few moles get consumed, the amount hardly changes. So remember this, that water is always a constant in aqueous solution. So never write water in the expression because it's a constant. I mean, there's no point writing the concentration of water in the expression because it's not going to change, or it's going to change, but very, very slightly or negligibly. So never write water concentration in the expression. It's taken as a constant. So anyways, all these Ligand exchange reactions, they would have a K stability value. Now, a lot of things depend on this K stability value. So so the point is that if the K stability value is high or is large, then a large value indicates that more products would be produced. I mean, if it's large, the reason it's large is that the equilibrium produces a lot more of the products and a lot fewer of the reactants. So large value means that there will be Ligand exchange. It's going to go in the forward direction. So a large value indicates you'll have more products and you're going to have less reactants. So that indicates more forward reaction, more Ligand exchange would take place. Nadine, I'll post these notes, Tika, after this class. Now, so large value indicates that there would be more products. I mean, that's why equilibrium constants are going to have a larger value, because there will be more products. So that means that also indicates that the product is more stable as well. Like it's easy to form the products. So which is why the product is more stable. Ibrahim, we're just ending transition metals, okay? I've posted the video lectures of all the transition metals. Then we'll move to the next topic, okay? Whichever we decide, say, yeah. अच्छा फिर ये कि the next thing is you've got I mean the vice versa, it's the opposite. If it's small, then that would indicate that there would be more reactants. Okay, we're going to start the next topic in a couple of days. More reactants and less products, and everything is vice versa. So that would indicate that there would be more backward reaction, or the equilibrium is shifted to the left, and that means that the reactant are more stable. So that's all about K stability. That K stability is the equilibrium constant for a Ligand exchange reaction. A higher value would indicate more products. A lower value would indicate that there are more reactants, that the Ligand exchange is not taking place. And never write water in the expression. That's especially when it's aqueous. Never write water. So we're going to move towards questions now. I think we're done with the chapter now. We're going to move towards the equation. So the first thing is, so let's start with the questions. And remember, they're very typical questions. So especially the Ligand exchange questions. So starting with the first one, he's saying there's an aqueous solution of copper sulfate. There's blue colored copper, and with water, 6 water molecules, complex ion. Separate portion of this blue solution react with aqueous NaOH and with concentrated hydrochloric acid. Give the following information for each of these reactions. So the first one is what happens when the reaction is with aqueous sodium hydroxide. So what happens is, remember we wrote down this reaction, copper with 6 water molecules. It has a charge of +2. So when you have 2 OH ions coming in from NaOH, there's going to be a Ligand exchange where a precipitate of copper hydroxide would be produced with 4 water molecules. And this is going to be your pale blue precipitate. So it's going to be a pale blue precipitate, and 6 water molecules are going to get knocked, or 4 water molecules are going to get knocked out.
सिर्फ प्रोडक्ट जो है, I mean, ये हमें याद करने होते हैं कि गैस करने होते हैं या खुद बनाने होते हैं?
मैं इधर बता दूं, एक सेकेंड, जस्ट अ सेकेंड. ठीक है, just a quick recap के अच्छा this. अच्छा, remember when copper ions are added to water, what happens is that the copper, which is positively charged, attracts all the lone pairs of water molecules and gets surrounded by them. That's known as a copper complex. That's known as copper with 6 water molecules. Ibrahim, is this clear?
Yes, sir.
So now what happens is when you add, this is known as a ligand. This water molecule is known as a ligand. When you add an ammonia molecule to it, ammonia is a ligand as well. It's got lone pairs as well. So what happens is that the water molecules, they start getting knocked out and they start getting replaced by ammonia molecules. So that is known as a ligand exchange reaction. So then in this case, he's adding OH ions. So, I mean, if you add dilute OH ions, dilute NaOH, this is what happens, that the 6 water molecules, they get replaced by OH ions. That's copper with 2 OH ions and 4 water molecule. And that's an insoluble pale blue precipitate that is formed. Now you have to remember all of this for copper. If you add Cl is another ligand. The 6 water molecules, they get knocked out and they get replaced by 4 Cl minus 1 ions. That's a CuCl4 minus 2 complex. That's greenish yellow in color. So you have these 4-5 types of complexes that are formed with copper. And with cobalt, you're going to get similar reactions as well. So you have to remember that for CLINs are bigger in size, so only 4 of them are surround them. That's a tetrahedral complex. For the other ones, it's usually an octahedral complex. 6 ligands, they surround it. So you have to remember these specific ligand exchange reaction. This one, the type of reaction, that's a precipitation reaction, because a precipitate is getting formed in this particular reaction. And color and state, we already wrote down the color and the state. The next one is with concentrated hydrochloric acid. So it's copper with 6 water molecules. And this time there would be 4 CLINs. And they're going to replace so it's going to be CuCl4. Copper ion is going to get surrounded by Cl minus 1 ions. And the 6 water molecules are going to get knocked out. So this one is a ligand exchange reaction. And the color of the complex is greenish yellow. I'll just add this to the notes as well, that this specific reaction where OH ions, that's known as a precipitation reaction. So because what happens is, I told you previously that when complexes become insoluble, they usually lose their water molecules to form an insoluble precipitate. They no longer remain a complex because they form an ionic lattice and they just simply leave the solution. So they leave the water molecules behind. Copper with OH ions becomes a neutral compound, and it no longer basically attracts water molecules anymore. So it turns into copper hydroxide, which is a solid precipitate. So this is known as a precipitation reaction, because the water molecules eventually they drop off, because copper plus 2, OH minus 1, it is now a neutral compound. So it would no longer attract the water molecules and it would turn into CuOH2. So that's the first one, TK. We did this. Is this clear? This one?
Sir, where we wrote copper hydroxide and OH2 and water 4 molecules, we could also write that copper hydroxide solid and then 6 water molecules get knocked out.
You can do that. Yes. TK. And remember, it's I also told you that they're going to accept both of them. I mean, the marking schemes usually accept both of them. TK. So then, and we wrote down the somewhere we wrote down the proper ligand exchange reaction somewhere, which was, I think, this one. I mean, this is, I mean, we wrote this, that, just a second, this thing. That when you add a few drops of NaOH, 2 OH ions, copper hydroxide is produced in 6 water molecules. So this is the equation that you were talking about, TK. Now the next one is, I think that's more to do with, let's leave the moles questions for now. Let's move to the just stick to the transition metal questions. Copper 2 ions, write down the electronic configuration. So copper is 1s2, 2s2, 2p6, and then it's, I think, 3s2, 3p6. Copper is that special case where the 3d gets completely full and the 4s is 1 electron. So it's 2 plus, so this is gone, and this is going to have 9 electrons. State the color of the solutions of the following ions. Remember, it's typical questions, TK. It's going to be greenish yellow. These are the latest questions. I think these are 2020 papers. And this one is blue solution. What about the next one? He's saying octahedral complexes of copper 2+ with different ligands can have different colors. So it's a 2-mark question where you just have to explain why changing the ligand is going to change the color of the complex. So this is something that we did. Okay, why are transition metals colored? So I told you that when the copper ion gets surrounded by these ligands, it's got these inner subshells that includes the d subshell, and the d subshell are two types of d orbitals. One are between the axis, one are on the axis. So when you have an octahedral complex, the ligands, they stick to the copper on the axis. So it becomes a lot harder to keep electrons in the green orbitals, a lot easier to keep electrons in the pink ones, which is why your d subshell splits into two energy levels. Harder to keep electrons on the axis, easier to keep electrons between the axis. So there's an energy gap, and that energy gap exactly matches frequencies. Energy is proportional to frequency. So this energy gap, the electrons can jump from the lower energy to the higher energy. And this energy gap specifically matches frequencies that belong to the visible spectrum. Delta E matches frequencies that belong to the visible spectrum, which is why you see complementary colors when the electron jumps from the lower energy to the higher energy. So what happens when ligands change? This is something that we did as well. We did write this. So I'll just, this one. Why does change of ligand changes color? So the answer to that was different ligands, lone pairs exert a different amount of repulsion, which creates a different energy gap as the D subshell splits. And since E is equal to HF, a different frequency is absorbed from the visible spectrum. And I think we should complete this. This looks slightly incomplete. I mean, we did write it above, but I think I'll just complete it over here as well. From the visible spectrum, what happens when electrons move from the lower energy? Lower energy D subshell to higher energy D subshell. To higher energy D subshell. So now the thing is that so why does the ligand change color? Because the energy gap is going to be different. So remember, previously all the D subshells would degenerate. They had the same energy levels, but now they're going to split. And it depends on the ligands. How much repulsion they cause, that would create this energy gap between the two sets of D orbitals, the ones that are between the axis and the ones that are lying on the axis. So that's your typical question for the answer for this one. And I mean, for this, I think we should also simultaneously open. I mean, just a second. This is summer 1942. Just 1 second. Since it's a 2-mark, remember the number of marks, they kind of vary. In this case, it's just 2 marks. So we're just going to check what were the 2 important points that we had to write. So I think this is the question with the D subshell. Or maybe not. Just 1 second. So explain why that's question number 1. Yeah, I think it's yep, this is, they just gave you 2 marks for this. that delta E is different. So it was just 2 marks there. So you had to write a short. I mean, we wrote the full explanation. It could have been a 4-mark question, so you would give all the details, but this was just a 2-mark question, so they just gave you 2 marks for that. The delta E is different, energy gap is different, and they didn't ask for the reason. And a different frequency or wavelength is absorbed or transmitted, which I think did not write. So I think we should. We didn't talk about the since E is equal to HF, a different frequency. We didn't write that, so that's there. So that's like the full complete answer if it's a 3-4 mark question, but over here it was just a 2-mark question. So they were just looking for 2 points. Now the next one is why are copper 1 and silver 1 salts are colorless? So what's the reason for that? Now the reason for that is especially copper 1 salts. Now when you have copper 1 plus salts, the electronic configuration of a copper 1 plus salt is 3s2, 3p6, it's got 3d10, and the 4s is 0. Now, when you have a copper 1 salt, and why is it colorless? Because the 3d subshell is full. So in this case, the D subshell is full. What difference does that make? When the D subshell is full, even if the D subshell splits, the electron cannot move from a lower energy to a higher energy D subshell because there's no space available there. If this was 2 electrons as well, the electron can't transition from this point to this point because there's no room available. So you need the D subshells to be incompletely filled. So the 3D subshell is full. So electrons cannot gain energy and move from low energy D subshell D orbital, sorry. D orbital to higher energy D orbital. So that's one. The electrons wouldn't be able to do that, and cannot therefore gain frequencies from the visible spectrum.
So can you explain this point कि ये electron transfer?
For silver, I'm not sure. You would have to write the electronic configuration of silver. I'm not sure how many electrons it's got, but it would be the same, probably the same thing. Silver plus 1 would probably have a full D subshell as well. I mean, I would have to check which. I mean, you can write the electronic configuration, but silver would also have a full D subshell. Achha, Brad, this is the.
2 marks का है.
Huh?
ये 2 marks का question है, उसके लिए इतना बड़ा आंसर तो नहीं लिखेंगे, सिर्फ एक कॉपर और सिल्वर का लिख देंगे. Point.
नहीं, एक तो 1 mark would be for the 3D subshell is full. Okay, the other one is the electron can't. I mean, we can check we just have the mark scheme with us. So the 3D subshell is full, that's 1 mark, and no electrons can be promoted, that's the other mark. So we did write those 2 points. Is this clear? Sam, I mean, for copper, the thing is that copper 2 plus iron, that has properties of transition metals. Copper 1 plus does not. Okay, so according to the definition, a transition metal was one which could form, which would form stable ions with incomplete D subshell. So it can form copper 2 plus. That is colored, but not copper 1 plus. So I mean, copper 1 plus is not going to show colored properties and other stuff. Isa, is this clear? This thing?
Yes, sir.
So Ibrar, the whole point was you have a D subshell. Okay, this is what a D subshell looks like. Somewhere we did draw. So this is what a D subshell looks like. That it's got 4 lobes. So electrons could be between the axes in different planes. They could be lying on the axis. And this is the 3DZ square. So you've got 5 types of D orbitals, just like your PX, PY, PZ. There are 5 different orientations of a D orbital. That's a total of 10 electrons that can accommodate. So you got electrons. So you've got a D subshell. Remember, copper ions are attracting all these ligands to it. So there's this D subshell that's sitting inside it. And because of the ligands approaching on the axis, it kind of becomes harder to keep electrons on the axis. And it kind of becomes easier to keep electrons between the axis. So the D subshell splits. Ibrar, is this point clear?
Yes.
So now what happens is that the D subshell is incompletely filled. For transition metals, the D subshell is always, when it forms an ion, it is incompletely filled. So electrons can jump from the lower energy to the high energy, which basically means the electrons can jump from the pink ones to the green ones, but they would have to gain energy because there's a lot more repulsion in the green ones. So electrons can jump from the lower energy to the higher energy, and they would absorb a specific frequency that belongs to the visible spectrum. The energy gap is always proportional to frequency. So if the energy gap is larger, a higher frequency is absorbed. If the energy gap is smaller, a smaller frequency is absorbed. But whatever is the case, the D subshell splits and the energy gap exactly matches frequencies that belong to the visible spectrum. And you see a complementary color. So if the transition metal absorbs red, you're not going to see red. You're going to see the colors that it's going to reflect, which is basically the rest of them. So this is why transition metals appear to be colored. Now, the point in this question was that for copper 1, the D subshell was completely full. If it's completely full, electrons can't gain energy and move to the higher energy D subshells, D orbitals, because they're already full. So you can't make this transition. The electrons can't be promoted. So which is why they will not be gaining any frequencies from the visible spectrum, because the transition would be impossible to happen. So now the next one is, this is probably about Ligand Exchange. They've got KSP as well. So the equilibrium constant for equilibrium 1 is the solubility product of AgPr. The equilibrium constant for equilibrium 2 is the stability constant for the formation of AgNH3 2+. Calculate the solubility of AgPr at 298 Kelvins in mole per dm cube. So, and using Lee, so this one, we can try doing this one because it includes solubility products. I'll just solubility product is the equilibrium constant for this reaction. AgPr is an insoluble salt. Remember, solubility product is not related to transition metal, so I'll just explain briefly what this is. So you got AgPr, it's dissolving, forming silver ions and Br- ions. Now, solubility product is when you have a salt and it's dissolving and it's forming a saturated solution. That means it's going in the forward direction, but at the same time, it's forming the precipitate back again. So it's also going in the backward direction. So the solubility product would be the equilibrium constant for this specific reaction, which is product concentration, which are Ag+1 and Br-1 aqueous, divided by the reactants, which is AgBr solid. Now solids have constant concentration, so you don't write them in the expression. So that's your expression for KSP for the first one. Now he's asking for the solubility. So the solubility is, so we're going to try and calculate the solubility, which is basically how many ions would exist in the solution. So if the solution contains X amount of silver ions, it's also going to contain X amount of Br-1 ions, because both ions are going to be produced in the same ratio. So if I dissolve 10 moles of AgBr, there would be 10 silver ions and 10 Br minus 1 ions. If I dissolve X moles of AgBr in this solution, there would be X Ag plus 1 ions and X Br minus 1 ions. So I have the concentration of silver ions as X, and the concentration of Br ions would be exactly the same. Remember, if you dissolve a salt, both ions would be produced in exactly the same ratio, which is, so the unknown number is, we don't know what the concentration is. So I've taken it as X. So it's X into X, which is equal to KSP, which is given as 5 times 10 power minus 13. So it's basically X squared. So it's 5 times 10 power minus 13. And you underroot that. What do you get if you underroot that? I mean, is this part clear? We haven't done solubility product, but is solubility product clear?
Yes, sir. And the answer is 7.0 into 10's power minus 7.
The 7.07?
Into 10's power minus 7.
7.07, right?
Yes.
Achha, so we figured out the concentration of silver ions and Br ions. I took it as X, and we figured that out. So the solubility of AgBr is that this much is going to dissolve 7.07 into 10 to the minus 7 mole per deci.
Yes, sir. We would find the concentration. So what is the difference between the two?
Between what? Between?
Like we basically did it the same way we do the concentration, right? K stability, the way we do that, we did it the same. So what's the difference between the two?
I mean, both of them are equilibrium constants. TK, the application is different. Solubility product applies to substances that are dissolving in a solution. Like if
Okay.
TK, so it has a specific application. We're going to study that later. TK, so solubility, I mean, don't focus too much on solubility product, but solubility product is when you have a salt and you're trying to dissolve it in a saturated solution. So it would reach an equilibrium. I mean, if you try to dissolve NaCl in water, it will dissolve up to a certain point. Once it becomes saturated, the more you try to dissolve, the more precipitate would be formed back again. So it's going to reach equilibrium. So solubility product is the equilibrium constant for this specific reaction. Stability constant is the equilibrium constant for a Ligand exchange reaction. Like this one is a Ligand exchange reaction. You have silver ions, aqueous, and NH3 comes in. Now, silver aqueous means that there's water, there's a complex with water that's forming. They don't write water in the expression. Why? Because I just told you that water is in excess. So when you calculate equilibrium constants, the water, I mean, you just cut out water because its concentration is a constant. So a lot of times they don't even write water in the expression. So silver ions aqueous, NH3 comes in, and NH3 replaces the water molecules. So this one is equilibrium constant for a Ligand exchange reaction. Minus, I'm not sure. It's I mean, it's up to you. I don't know. I didn't calculate this. You can double check this. I think it's on -7. I think, but
I'm getting -7.
-7. So it's -7. So let's continue with this question next time. Hopefully you got what solubility product was. It's not part of the thing that we just studied. We're going to try and solve this particular question. That it's mainly about K stability. So we'll solve this tomorrow now. Okay. So let's continue tomorrow, and I'll try and send the notes shortly.
चलिए, okay, sir. Allah Hafiz.
Thank you, sir. Allah Hafiz.
Allah Hafiz.